Hi, my name's Daniel Balti and I work for the Functional Magnetic Resonance Imaging of the Brain Centre at the University of Oxford. I'm a physicist by training, but I've ended up working straddling multiple disciplines between medicine and physiology and physics and mathematics. What I'm going to try and explain to you today is a little bit about how MRI works, and more specifically about what we do here in Oxford in particular. The way that an MRI scanner works is totally different to the way that an X-ray machine works. The human body is full of water, and a water molecule consists of 2 atoms of hydrogen and 1 atom of oxygen. Hydrogen, being the simplest element in the periodic table, consists of just a single proton for its nucleus and is orbited by a single electron. And if we consider that this is an example of a single proton, as well as having a certain volume and a certain mass and a positive charge, it also has what we call a magnetic moment, which means it's a little bit like a bar magnet, or the Earth, in that it's got a north pole and a south pole. It's also similar to the Earth in that it has what we call spin, which means it's spinning around. And so I'll represent the North Pole by attaching this screw. And just like the Earth, it spins around its magnetic pole. Now normally it's just sitting there happily spinning, but if you place it in a magnetic field, what it's going to do is it's going to start what we call precessing, which means that there's going to be this sort of like rotating top motion of that magnetic pole. And it's not just going to precess at any rate, it's going to precess at a very specific rate that is dependent by the field strength of the magnet. The magnet that we have behind me is a 3 Tesla scanner. Tesla is the unit of magnetic field strength. So if you can imagine that one magnet will pick up 1 kilogram and another magnet will pick up 2 kilograms, then that magnet is twice as strong. This magnet is about twice as strong as a normal clinical scanner, which has about 1.5 Tesla as its field strength. So when this is placed, this water proton is placed in the magnetic field, it starts to precess, and it's doing it at this particular frequency. This could tell us some information about the water or the environment that the water is in. But the problem is that we can't see this tiny magnetic field because it's being swamped by the huge magnetic field that we're creating with a scanner. It's kind of like trying to see a candle in front of a spotlight. The small light is just completely overwhelmed by the large light. But what we can do is, by applying a second magnetic field, which is perpendicular to the main field, the proton is going to want to try and precess around that as well. But if we apply a very small field, it's going to precess quite slowly. And so we apply the field for a short period of time, and it will tip over a little bit. And if we then turn the field off just as it gets to that point, this proton is now going to continue to spin around the large field. And now with the large field vertical, and this in a different plane, we can put a detector out to the side and we can see this rotating magnetic field. And it's going to be rotating at that very special frequency. And so that is now giving us an amount of information about how many protons have been affected in this magnetic field. And so that gives us a signal, but we really need some information about the tissue that we're looking at in the human body. And fortunately, the rate at which we go from this state, which is actually quite a high energy state, and the proton doesn't like being there, and any jostling or any effects on it, we're actually going to allow it to tip back to its low energy state where it would prefer to be. And so we get information about the thermodynamics of the system, how much energy is in the system, how much heat, how many other water molecules or other molecules there might be in the system. And so with that we can get a contrast. We can tell the difference between different tissue types. We can tell the difference between muscle and fat. We can tell the difference between kidney and liver. Or even within the brain we can tell the difference between grey matter and white matter. Grey matter is a lot more energetic, there's a lot more going on, there's more blood flow, it's effectively hotter. And so that knocks the signal down much faster. And so when we look at an image, we get this grayscale black and white image where areas that are darker have got a lot more thermodynamic activity going on. And so we get that contrast between the different tissue types. What we do specifically here is we're looking at functional brain imaging. So we're not just trying to take a picture of the brain, but we're trying to watch the brain in action as it's working. And fortunately, when you use an area of your brain, it increases the blood flow to that area. And blood is carrying oxygen on molecules of hemoglobin, and hemoglobin has iron in it. That's the reason why blood's red. It's just like rust. And the magnetic properties of hemoglobin change when they've got oxygen attached to it or not. And so when you change the amount of blood flow to a region, you're changing the amount of iron that's flowing through that region. And so you're changing the magnetic and thermodynamic properties of the area. And so if we look at a person's brain while they're just lying there not doing anything, And then we look at a person's brain when we're flashing lights in their eyes, or getting them to perform some sort of manual task with their hands, or do calculus, or anything that requires a specific task for your brain to perform. You'll change the blood flow to that area of the brain, and we can see the difference magnetically between the resting state and the active state in the brain.